So I want to finish up, start by finishing up with the discussion of the Friedmann equation, or rather discussing the Friedmann equation, which we actually hadn't done. So we had derived the equations of motion for this very simplified kind of space-time, spherically symmetric and so on, with spherically symmetric dust in it. But the equation as we wrote it was, as we finally, as it came to us, was like this. Okay, just reminding the equation that came from varying the action. But this equation is, of course, it's not really a local equation because it has quantities in it like the total mass of the universe. Whereas we know that ultimately this is just a version or some components of the Einstein equations, and the Einstein equations are local in space-time. In fact, of course, we haven't really derived them yet, but when we do derive them, we'll see that they are local because basically they come from a variational principle where the action functional that you vary is just an integral of a locally defined scalar, Lagrangian as you might call it. And in fact, we saw that here also in this special case, that the action functional we dealt with was essentially the integral over space-time of some locally defined quantity. Of course, in this case, the spatial integral was easy to do, and so we didn't even see it explicitly. It just amounted to a multiplication by the total spatial volume. However, so the equations of motion should be able to be cast in local form. So it really shouldn't matter what the total mass of the universe is. All it should really depend on, by this means the total mass of the dust. It shouldn't depend on that, something like that. And so if we want to, so it's worth putting this in local form, and then it'll be more recognizable to you. Those of you who are familiar with the so-called Friedmann equation, it'll be more recognizable in that form. So to do so, we want to divide basically by the 3 volume. So just for convenience, I'll divide, the 3 volume is of course proportional to the radius of curvature cubed. So just for convenience, I'll also divide by this 2 pi squared. So if we remember beta was defined, how was beta defined? Does someone have, it was some multiple of, here it was, beta was defined as 6 pi squared over kappa, the rationalized gravitational constant. So if we divide it by 2 pi squared, then that'll just equal to be 3 over kappa. And similarly, the other thing that we, the total mass divided by 2 pi squared a cubed. Well, remember, why did I put this 2 pi squared here? Because 2 pi squared a cubed is, if you remember, the volume of the 3-dimensional sphere, the spherical space at a moment of time. So when we divide the total mass by that, we just get the mass density, which I'll call here rho. That's the density of mass, that is rest mass of these dust particles, okay, which is also, in this case, because the particles are locally at rest, it's also the energy density in that matter, okay? So those are the 2 things. If we plug those 2 things, this would also be when we come to discuss the stress energy tensor, or from what you know from special relativity, and the stress energy tensor is the same object really, is this is also would be T00 if you use the natural coordinate system aligned with the cosmic rest frame and using proper time for time, which we have done. So this is the energy. So this That's what becomes of the term in M. And so when you put everything together, then you get, when you write all the terms out, you get minus 3 over kappa from this. Then we divide by a cubed, so it becomes 1 over a squared. So it becomes 1 over a dA d tau squared minus, again, the 3 over kappa a squared now. There was one factor of a here, just like here. So actually, it's just beta a again. So it's this expression, minus 3 over kappa a squared, plus rho, we said, and then the 2 pi a cubed cancels out, and we get plus lambda equals 0. This is called the Friedmann equation. This is usually what's called the Friedmann equation. Of course, it's equivalent to the equation we had in this case. But this is now a local equation because it has only cosmological constant, the local energy density, and some local curvature expression. This, of course, looks like a global expression, but it can be traded for, it's just a multiple of the scalar curvature of the space-like hypersurface. So it's also in that sense. Well, actually, we're actually in the context now that I remember of this Friedmann universe, or Friedmann cosmology. So I could just say it another way. This is the radius of curvature, and that's a locally defined object, which happens to be the same by assumption everywhere throughout space, although not, of course, time. This thing, of course, this 1 over a dA d tau has a name. It's called the Hubble constant, or if you want to be more correct, since it's not at all constant, it's the Hubble parameter. So this is the h that you always see in cosmology. So this thing is really minus 3 over kappa h squared. That's about, let me put it off to the side. That's all I wanted to say, except to give some sort of a mnemonic about how you can think of the terms in this equation. The way to think of this equation, and this is actually in some technical sense literally true, although we haven't done that yet, it's literally true that insofar as the energy is defined for a spatially closed cosmos, which is what we have here, the total energy must be regarded as being 0. And what happens in relativity is that in situations where the total energy is well defined, it's expressed by some sort of surface integral at infinity or at the boundary of space. And since space has no boundary in this case, it's just a 3-sphere, that surface integral is trivially 0. Okay. And so in some sense, the total energy is 0. And since we're dealing with a spatially homogeneous situation, the energy density would be constant, and therefore it would also have to be 0. So one can think of this equation. It's true that in general there's no well-defined energy density in gravity, where you have to include the energy of both the gravitational field and the matter. There's only this well-defined stress energy tensor. The gravitational contribution to the energy density is not a well-defined thing. It can be defined, but there's a large arbitrary element in how you define it. All that really in the end is objectively meaningful is the total energy. So that's one very traditionally confusing or troubling aspect at first to the notion of energy. It doesn't quite, it can't be localized in gravity. And this is ultimately a direct consequence of the equivalence principle, which says that the gravitational field, so to speak, can be made to vanish anywhere at any given point in space-time by an appropriate choice of coordinates. But leaving all that aside, this is, as I said, really a mnemonic device, a device to help you remember what the terms and how to think about the terms. And so in this case, since it's spatially homogeneous, we can just think of the energy density as the total energy divided by the volume, which is 0. So this is an equation that tells us that the total energy density is 0, and that's one way you can think about the Friedman equation. And then it helps to interpret the individual terms. Well, this is literally the energy density. I mean, this is, in the strict sense, an energy density of the dust. This you can think of as a contribution of curvature you could think of this as a contribution of the gravitational field. In this case, it's a contribution of the spatial curvature. And the only thing, I don't know how you can remember this 3 over kappa, but and I'm not even sure I'm not sure of a good intuitive reason why the sign has to be negative, but if you know enough other facts, you can relate it to them, like the existence of if you know that as we saw, that the nature of the solution, as we saw last time, the nature of the solution is to expand, reach a maximum radius, and then recontract. If you imagine everything at the moment when the radius is at its maximum, then this will vanish, dA d tau, and this is necessarily positive. And that solution we found was for 0 cosmological constant. So therefore, we better have a minus sign here. So in some sense, it's telling us that positive spatial curvature counts as negative gravitational energy density. Okay, so that's that term. And this term, of course, you can think of as the kinetic energy in the gravitational field or in the metric. And as I mentioned, as I harped on, as I stressed last time, it comes with the opposite of the sign that you would have expected. So if you want to think of this as an energy equation, you want this to be positive because it is positive. So you want to keep the signs like this, and then this comes out negative. And this tells us, then finally there's the cosmological constant, and then it tells us that from the point of view of this equation, we could think of it as a vacuum energy density that's there even when there's no ordinary matter. And so people sometimes call it a vacuum energy density. This is the way I think most cosmologists think about it. That's why they use words like dark energy to describe this, because in the Friedman equation, it looks like an energy contribution. So this is kinetic. This is potential energy, if you like, of gravity, coming from curvature. Kinetic energy. So that's all I want. If we were to write the same equation, you may these days not see this term in the equation very often, and that's because people are often, just from the beginning, assuming a spatially flat space-time. It's clear that this will go to 0 if the radius of curvature goes to infinity, which is the spatially flat case. Okay. So any questions on any of that or on any of the work we did on cosmology? Yeah.
What happens to the kinetic energy term when A goes to infinity?
Well, you see that the A is both in the numerator and the denominator. So that doesn't necessarily vanish. In general, it will not vanish. What this represents is the local rate of change, the local rate of stretching of space-time, or whatever the opposite of stretching is. I should say of space, really, stretching of space.
But the balance of A and the denominator blowing up.
So they both blow up if you like, yes. So that's actually a good question in the sense that it points out that even in the case of the flat, spatially flat universe, people use the same notion of A. So what the hell do they mean by A? I mean, if it's supposed to be infinite, this infinity over infinity is not very well defined. They still use A and they still call it the scale factor, but now it has an arbitrary normalization. It no longer has a direct physical meaning. It's only the ratios of A, sort of A at one time tau 1 to A of tau 2 that have meaning. So it now requires an arbitrary normalization, and it's really it really has no meaning directly, but its ratios still have meaning. They tell you the amount by which the universe spatially has expanded or contracted between one moment of cosmic time and another moment of cosmic time. It's most traditional to set A to be 1 now, but you don't have to do that now, meaning in the cosmic now. But you can actually set it to be 1 anywhere, right? So there's a little bit of a fake in this A, in the sense that it's not a well-defined parameter anymore. It contains an arbitrary overall scale. But since it occurs in this special combination, multiplying A by any overall constant doesn't change this Hubble parameter. So that's a good question. So in fact, you most often see it written probably without this. You would just see it with this replaced by h, right? Or h squared. But if you ask someone, what is h squared? They'll say, what is h? They'll say, it's 1 over a dA d tau. Then you say, what is a? And then you get a kind of confusing answer, or something along the lines that I just said. So there's also the case of the negatively curved Friedmann cosmos, which is sort of hyperbolic space at a given moment of time. There again, you can interpret A as the radius of curvature, although the curvature is now with a negative sign. But in the special case of flat, it has no genuine local meaning. Any other questions? Okay, so now I get on to the next section, so to speak, of the course, which I've called rudimentary. I won't write it down, but gravitational kinematics. What this really means is we have to develop a fair amount of mathematics that allows us to describe manifolds of a much more general nature than the very special highly symmetric ones that we've been dealing with so far. And that means we'll have to define the notion of manifold, the notion of smooth manifold, the notion of metric, space-time metric, and the notion of causal structure. This is kinematic. So this is sort of kinematics in this Takatonic classification. If you remember from the first day, it would sort of be the second stage, thinking of the phenomenological stage as the first, kinematic as the second, and dynamical as the third. The dynamics, of course, will be the Einstein equations, but that'll be still later. So what we're really doing here is, what is the right mathematical description of a gravitational field in the generalized sense in which it occurs in general relativity, the primary actor in general relativity? What it can be basically follows from the equivalence principle. So the equivalence principle, which is, of course, just really, although some people try to give it a more precise formulation, I think it's probably best to think of it as a heuristic principle that led to general relativity. But once we have general relativity, what it's replaced by is the statement that space-time is a differentiable manifold with a Lorentzian metric, and we want to see now exactly what that means. So at the heuristic level, though, what it says is that space-time is locally like the space-time of special relativity. That's essentially what the equivalence principle says. It's like four-dimensional Minkowski space. So if we want to understand what the kind of manifold that occurs in general relativity is, we should just take this to heart and just think that what it would really mean to be locally like Minkowski space. To see what that could mean, we have to think, well, what is it to be like Minkowski space? In other words, what are the mathematical or physical, ultimately, structures that characterize Minkowski space? So we can isolate 4 of them, sort of building from the ground up. First of all, Minkowski space, of course, it's a 4-dimensional space. Therefore, it has a topology, and it has the topology of R4. It's just, if you like, it can be parameterized or coordinatized by 4 coordinates that run from -infinity to infinity. Okay. So, second of all, it is not just a 4-dimensional thing, it's a flat 4-dimensional thing. So in the technical language, that means it's a vector space. It has this vector space structure. What does that mean physically? For example, it means that you can add displacements in Minkowski space. So, for example, if you think of 4 momentum is a 4 vector. If you imagine a collision in conservation of energy and momentum, that's conservation of 4 momentum. It means that the sum of it says that the sum of all the initial 4 momenta equals the sum of all the final 4 momenta. Okay. So when I write this sum, I'm adding vectors. The fact that I can do that is because Minkowski space is a vector space and not just some sort of floppy 4 manifold. Third of all, of course, this is the one that's sort of most on the surface or most evident, usually when you think about it, is that there's a notion of distance, and especially a notion of proper time, distance, a notion of light ray, which is a special null direction in Minkowski space. And that's all to say that it has a Lorentzian metric, right? So it's not a metric in the sense you might often find it in mathematics books, which would want all plus signs here. It's not, but it's a metric, as we call it in physics. And then finally, it has a causal structure that tells, of course, which events in space-time in Minkowski space can influence which other events in space-time. So this is all special relativity. This is the structures of Minkowski space. They all correspond to one of the features of the more general kind of manifold that features in general relativity. So the fact that this is basically the statement that as a topological space, Minkowski space is 4-dimensional. And so there's a similar notion for the manifold, and it's what it tells us that space-time, before we even think of the other properties, is what's called a topological manifold. I wrote here C0 because I could have written some other thing. I don't even know if I'll bother to define what this means. It's just another way of saying that it has a local topological structure. We haven't. Well, let me not say anything more about it for a couple of minutes. So the generalization is that this 4-dimensional vector space can become a manifold, but the manifold still has a topology. Locally, it's still 4-dimensional. That means that it still locally looks topologically indistinguishable from some portion of Minkowski space. Second of all, Minkowski space is a vector space. Here the 4-dimensionality, here the statement, when I say that it's locally like Minkowski space, that has a technical meaning. It means that every point in the manifold has a neighborhood, I'll say what that means in a second again, that is isomorphic to some neighborhood in Minkowski space. The vector space structure doesn't quite survive as well. It's not true that at every point in space-time there's a neighborhood which has a vector space structure. What's true is that it survives only infinitesimally. So so it's like every point has an infinitesimal neighborhood that's like a vector space. That is a vector space. And we call that the tangent space. And the technical word for this is that the space-time is a manifold with a differentiable structure, usually called a differentiable manifold. And what about the metric? Well, the metric goes over to something. Of course, this was a flat metric. It goes over to a curved metric. So it's described not just by a single tensor like it would have been here, A to A, B, let's say, but it's described by a metric field now, a metric which varies in some sense from point to point, which is equivalently also described by what's called a line element. You often see it written like this. That's this ds squared thing that you often see written down, and we'll define this precisely also in a bit. And then finally, it has a causal structure. Here the name is the same. It's still called a causal structure. But the patterns of causal relationships are now more general than you find in Minkowski space. But you still have locally distinction between future directions, past directions. The light cone structure is still locally the same, or more precisely, at each point, it looks the same as if it was in Minkowski space. So each tangent space to the manifold has the same light cone structure on it. So to introduce gravitational kinematics, then, is to just explain what all these things mean and give them precise definitions. So let me start with the first one, alpha, which is that space-time is a topological manifold. Okay. So what does it mean to say that it's a C0 manifold? Yeah.
Why do you distinguish between causal structure and when you have a metric, then the causal structure follows?
When you have a metric, it's true that when you have a Lorentzian metric, the causal structure follows to a very great extent. The only slight distinction is there's a sort of sign here. In other words, when you have a light cone, if you just have a metric, it tells you what are the time-like directions and what are the space-like directions and so on. But it doesn't tell you which is the future and which is the past. So if you like, you could say that I'm adding, this is called a time orientation. You could say that I'm adding a time orientation to the metric. And as I think we discussed a little bit, it's not certain, actually. It's not certain that microscopically the metric does have a time orientation in itself. It certainly does macroscopically. There's certainly a very big difference between the future direction and the past direction. But if we give it a causal structure, then usually it's taken to mean that you include a time orientation. But it's true that in the case of the space-time, once it's a Lorentzian manifold, it acquires a causal structure automatically. However, I've separated it out. We won't, and for that reason, we won't have to do much work to define this, or I won't take a big trouble to define it. I've separated it out for two reasons, one of which you can guess, right? I mean, one of the reasons is that these causal relationships play a very important role in some of the more sophisticated results, like the proofs of the singularity theorems, the proof of one particular proof of the total positive energy theorem. A lot of these depend on heavily on thinking about the causal structure in itself. It's that aspect of the space-time that becomes important. It's also obviously physically important. So for that reason, it seems worth separating. And then, of course, the other reason, the one which you would have guessed, is that from my point of view, this structure is actually more basic than this. So although in the usual developments, the way that seems natural in the continuum, you have the metric first and the causal structure sort of tags along. You could actually reverse it. If you have only the causal structure, you get 9/10 of the metric. You get what's called the conformal metric. You get the conformal metric up to an overall local scale factor, sorry. But of course, I think that in quantum gravity, it's the causal structure which will survive and continue to have meaning, whereas the metric will only become, will lose its immediate meaning and only become a derived quantity, which is the metric tensor will only exist in some approximation. So that's the other reason for isolating this. So what I also wanted, so some reading for this, what we're doing just now, is Wald's books, Appendix A, for things like definition of topology, and section 2.1, and Schutz. Now, here's the problem again. I have pages 151 to 156, which, if the section numbers have not changed, that'll be section 6.1 and section 6.2. Maybe part of section 6.2. Maybe not the very last part if you don't want to look at. If you don't want to look at that, so the discussion now corresponds to those. Hopefully, the section. If the sections have, if these don't make sense, then let me know, and we'll sort out what is the appropriate section numbers or page numbers in the edition that you have. Do you have the book there? So what is there a section 6.1? What is it called? Oops. What's it called? Manifolds? Manifolds. Riemannian manifolds. 6.2, 6.1. I think that must be the same. What is this 6.1? Yeah, this must be the same. That's good. So it's still section 6.1. 6. Yes, that's it. So that's still correct. So it's basically section 6.1 and 6.2. So when we say that space-time is a topological manifold, of course, to give that as precise meaning, I have to say what a topology is, and I'm not going to take the trouble to do that. If you want to see the exact, I could say the definition in a line, but either you know it and you don't therefore need it, or you don't know it and it won't convey anything at all to you. But I could say it, that it's a space provided with a set of a distinguished family of open sets, which is closed under arbitrary union and finite intersection. Then you can see what that'll do for you if you're not already familiar with it. But let me try and give some of the intuitive sense of what a topology. A topology is a notion of near, what I might call contiguity. Why have I used such a strange word? It's some fancy word that means nearness. I'm using it just to make it not try to have any of the implications of the usual word nearness, which usually presupposes a metric. In other words, that given 2 points, you can say how close these are nearer than this, or these 2 points. This point is nearer to that point than it is to that. That's just what you can't say in a topological space. You still have a notion of nearness, but it's a more subtle kind of notion, which basically has to be expressed in terms of the idea of neighborhood, which I'll probably usually abbreviate just to not write it always out, as NHBD, neighborhood, or equivalently, the idea of convergence. So I think convergence is actually, at least for me, the more intuitive notion. So although we can't say, given just 2 points in a topological space, we can't say whether they're really near to each other or far from each other. For that, we need something like a metric. And even, well, even in the Lorentzian case, there's a lot of subtlety connected even with that, because you have things that are points that are at zero, that are not the same point, but at zero Lorentzian distance along light rays. But also in a topological space, we don't even have the metric. But so therefore, we can't say whether they're objectively close or far from each other. But what we can still say is if we start this point to move, take a sequence of points, is the simplest way to do it formally, then we can say whether this point approaches to that point, whether it has this point as a limit or not. In other words, so given a sequence of points, let's call this one y and this one x, and now let's imagine as a function of time or discrete time x1, x2, x3. So we'll get a sequence of points. It is meaningful to ask whether that sequence of points approaches in the limit, goes over to y, or does not. That's what makes it a topological space. It can also be described in terms of the notion of neighborhood. So this is the notion of convergence. So a topological space, from this point of view, is a space in which the notion of convergence makes sense. Convergent sequence, in this case, makes sense. It can also be a space in which every point is provided with neighborhoods. So again, the intuitive idea, so let's take this point, which I called over there y. If we had a metric, if it was in R, if this space was in R4, and we used the Euclidean metric on R4, just the sum of the squares of the components of R4, the four coordinates of R4, then we could say, given the point x, what's a little ball around it of some radius epsilon? And if we take epsilon smaller and smaller, we would get smaller, if we start with big epsilon and make it smaller, we'd get a sequence of balls shrinking down to that point. Those are called neighborhoods. As long as epsilon is not zero, they're called neighborhoods of that point y. And again, there's no objective meaning to say, you can, if you just look at one of them, you don't know very much. But if you know the family of all the neighborhoods of that point, then you really have all the topological information. And the relation between, so another way of thinking about a topological space is one in which each point is provided with a family of neighborhoods that generalize these open balls in Euclidean space. And the relation between the two notions, the topological one, the convergence one, and the neighborhood one, is just what you might think. If you ask, what does it mean for a sequence? If you ask, what does it mean for a sequence of points to converge to this point y? If we had this distance epsilon, we would just say, you go think back to elementary calculus, where you'd say for every epsilon there exists a delta of such blah, blah, blah. Here it would be for every epsilon there exists an n. So this is 1, 2, 3. For every epsilon, there's some n such that if you go out beyond n in the sequence, you'll get within epsilon of that point y. So that means that if we translate that into the language of neighborhoods, it means that for every neighborhood, there exists an n such that beyond n the sequence is within that neighborhood. So that's the meaning of convergence. For every, so the xn converges to y if and only if for every neighborhood, let's call this neighborhood n, and for every that's like saying for every epsilon, and then we want to say there exists, and now I have, maybe I shouldn't call this n. Let's call this neighborhood u. Okay. For every u, there exists an n, an integer n, such that if little j is greater than n, then xn, xj, the jth element in the sequence, is within the neighborhood U. Okay. You haven't seen it before, you can think about it later, and you'll see that it corresponds exactly to this epsilon delta notion of convergence. So that's the relation between the two. So if you know what the neighborhoods are, you know what a convergent sequence is, and you can actually turn it around. If you know all the convergent sequences, you could know what the neighborhoods are. But I'm not, as I say, I'm not going to try and make everything very precise, because we'll be able to bypass a lot of these more general notions by using what are called charts. But the importance of topology is that it lets us speak of local. It makes sense of, let's say, of locality or local features. And so the idea, so when I said that a space-time manifold is locally like Minkowski space in a topological sense, then that turns out to have a precise meaning. We say that a manifold is something which is locally like, in this case, a four-dimensional manifold, which is locally like R4. By the way, R4 I haven't defined, but I gave you, if you remember, I gave you a list of a handout that had mathematical terminology and so on. And that so there are some symbols that I'm just taking for granted. If I use a symbol like this that I don't define, it should be in that handout. If it's not, let me know, and then I'll define it. Okay. So the fact having a topology makes sense of locality, and then the statement that spacetime is a four-manifold is that it's locally indistinguishable from R4 in the topological sense. This is one way. This would be a definition of a continuous manifold or a C0 manifold, but it would bring in a lot of abstract mathematics unnecessarily, because there's a quicker way of doing it. So instead of defining it that way, we can say, you see, suppose that you had a manifold. Suppose this were some manifold, and it was locally like, since it is a manifold, it's locally like R4. So that means for every point, I can find some neighborhood which is indistinguishable topologically from a neighborhood in R4. That means I can cover it with this neighborhood. And so another way of thinking about this is, let's start with these neighborhoods and then just glue them together to make the manifold. So we can say it in a different way. We can say that a topological manifold is one that could have been built up by gluing together little pieces of R4. And that's the way that we'll actually use it. So, so what we'll actually do is what are called charts. We'll say that we can build up the manifold by gluing together, by means of these so-called charts, portions of R4. This is actually doubly convenient, because not only does it let us define the topology, which is only really the first step, it lets us define the differentiable structure. And in fact, in the case of the differentiable structure, I don't know of any other way of defining it other than by means of these charts, or something that's, in the end, I think, not really something more general than them, but might appear to be. I'll leave that as a mysterious comment. But anyway, so basically I think this is the only practical way of defining the differentiable structure. That is the statement that is basically to define tangent spaces, which means that you can define locally vectors, and then in terms of vectors, almost everything you deal with some exceptions, is built out of vectors, namely that it's made from tensors. Okay, so that was a quasi-heuristic. Now I'm going to start being more rigorous, fairly rigorous, define the idea of the chart. But let me still say something about the general idea just before, then I'll summarize it in the definition in a precise definition of a chart. So so this picture looked a little messy. Let me make it kind of neater. So here's our manifold. Think of it as a surface. Of course, it's really four-dimensional, but think of it as a two-dimensional surface. It may have some holes, so to speak, in it, where it looks like a torus. And then we're going to find within it a chart that belongs to a particular neighborhood within the manifold, which I'll call U. And what the chart does is that it sets up this equivalence between this neighborhood and a portion of four-dimensional, some four-dimensional vector space, which is a Minkowski space is. Although at the moment we're not using the vector space structure, but this is some four-dimensional vector space. The chart I haven't shown you the chart yet, but I'll name it Xi. So I'll call this V sub Xi, the vector space that belongs to the chart Xi. And I draw this square to sort of indicate that it's a vector space. So what we want to say is that this portion of the manifold was made by, we said that the whole manifold is made by gluing together all these different portions of this vector space, or some isomorphic vector space. So the gluing is actually to be given by some sort of map. So we imagine cutting out this portion. So I'll call this is the portion of the vector space that corresponds to this neighborhood. So I'll call it U. So I'll call it U tilde. This may not look too, this is supposed to be a U. This is supposed to be a U tilde. Okay. And now we have some map, Xi, that takes points of the manifold M into the vector space V. Not every point of the manifold M, but those within this neighborhood, or this open set, if you want the technical word, U. So Xi, in some sense, converts a subset of a manifold into a subset of an n-dimensional vector space, where for us n will be 4. So here's a technical aside, if I'm not going to say. So we will assume, I guess I thought I might have said it later, but anyway, we'll assume that this U tilde will be open, what's called an open set. I don't know, do some of you remember the definition of so this is now an open set of a vector space. In particular, in many cases, this will just be the vector space R4. So does everyone know what I mean by that? An open subset of R4 or an open subset of a vector space? Yeah. So
what you want me to tell you?
Sure.
The way I've been dealing with open is just it's a set in your topology.
Oh, yeah, that's too general. Okay. So I want to know when we put the topology on R4, then how can we recognize which are the open sets?
Doesn't it contain boundary?
Yes, you know too much. Yeah, that's right. But then I have to define its boundary. That's right. You want to, yeah?
Like around each point in that set, you can actually find an open disk.
Yes, around each point of that set, that's the definition I would have given in this case. Around each point of it, you can find a little ball of radius, some epsilon, that's completely contained within that set. Then it's called open. So what it means intuitively, if you're not thinking of particularly bizarre examples of things, you just have some region like this, and then it is exactly as you said. To say that it's open is just that it doesn't contain its boundary. It's the interior without being the boundary points. It's just a mathematical technicality. It won't really play any role in what we're doing. But if you want to be precise, it has to be open. Now we want, so it's important that this gives the topological information to the manifold, so it's important that C be continuous, and furthermore, its inverse be continuous. Or it would be important if this space manifold already had a topology, but since we're just building the manifold, it doesn't yet have a topology, but we'll give it one in such a way, we'll give it one by inheriting it from these charts, and then once we give it that one, then both C and C inverse will be continuous. So it doesn't have to be smooth or differentiable or whatever, but it has to be continuous. So we'll define a manifold this way. We'll define a manifold as a union of these, strictly speak, of these U's. I should probably give this the label U, the subscript U sub C, and this I could call U tilde sub C. Another word for this is that U sub C is equal to what's called the domain of the map C, right? And then that is familiar probably to most people. U tilde sub C doesn't seem to have a good standard name, but some people call it the codomain of C. Sorry, whoops. That wouldn't be right. It's actually, technically speaking, V sub C, that's the codomain. So this is a map from this domain within the manifold into this other space, but it doesn't actually, in general, it will never almost cover the whole space. But so this thing is sometimes called the range. Anyway, the different terms, but just in case you run across those terms. So we'll define a manifold in terms of these charts. We just need enough charts so that these domains, U sub C, cover the whole manifold. So because enough pieces to glue them, to be able to, when we glue them together, produce the whole manifold. So we'll define the manifold by a set of charts, and the set of charts also is given a technical name, which is called, well, I guess that's a very reasonable name. It's called an atlas. I guess if you look in an atlas, you've got a set of charts or a set of maps, but map has too many other meanings in mathematics, so they use charts instead of map. So an atlas is a set of charts, sort of C, eta, blah, blah, blah. Each one of them covers some neighborhood of the manifold, gives us back, under this mapping, some piece of the manifold that we're piecing together. Once we have the charts, then we can actually define the topology on M. However, we can't do this arbitrarily. Now we need a consistency condition. Because suppose, it's fine, we have this chart here that gives us one piece of the manifold, and we have another chart somewhere else that gives us another piece. But we have to be careful when those pieces overlap. We need to say, if intuitively we're gluing them together, we have to say how we glue them together. And that we do by these so-called gluing maps. So let me give you another picture. So we now imagine, I guess I was using red for this. So now imagine that we have two overlapping charts, that is to say two charts whose domains overlap. So say this one and this one. So let this one be U C, and let this one be U eta. And that almost looks indistinguishable from, well, anyway. Then there'll be an overlap region, right? And in this overlap region, I'll give that overlap region, I'll give a name. I'll call it U. I'll call it U C eta. So that's the subset that belongs to both the domains of both charts. And it's, as you can see, it's the place where we've glued those two pieces of the vector space together. So there are two charts, so I'll draw the vector space twice, although it might be the same vector space. So this was VC, this was V eta. And so over here, there's an image of this, and over here, there's an image. So C is going, oops, something is wrong with what I've written. I switched C and eta in this. But anyway, this is C, this is eta. And so now, within this, this overlap region is present. And then the same overlap region is also present within this as a subset of the image of, I forgot to say, this, another word for this, I might slip into using this word. Another word for this U tilde C is also often called the image of Xi, which is a natural enough term. So now, let me define, right, so now, since if I take the same point, which I meant, so I should have, let me change this a little bit. Sorry for messing it. So let me take a single point, which actually is in the overlap region now, and ask where it goes under the action of Xi and under the action of eta. So this is the same point. So it's, I think I should redraw this. So now it has to go into the overlap region. And this one, likewise, since it's the same point, it has to go into the overlap region somewhere here. So we have two images of the same point. So if we think of constructing the manifold by gluing this and this together, this tells us where which points must be equated to which other points. In other words, how the gluing is to be done. So in other words, what I want to do is introduce a gluing map now that'll tell us, that'll take the one image of that point to the other one. I'll call that F sub Xi eta. And the condition on that point, if you look at this, if you think what it says that if I start with this point in the manifold and go by Xi, or if I go first by eta and then go by this gluing map, I must arrive at the same point. Therefore, the condition is F sub Xi eta, circle eta, is equal to F sub Xi, if I said that right. So that's the consistency condition for the gluing map. Also notice that F, according to my notation, F Xi eta and F eta Xi, once I've defined them this way, are inverses of each other, obviously, because they just take the two images of the same point to each other, so depending whether I think of it going this way or going this way, I just get inverse. Okay, so that's the intuitive idea. What?
The right-hand side of the equation, first one. Did you mean to write Xi or F of Xi? The other one. The other one.
Oh, I meant to write Xi. Sorry. Yeah, absolutely. I meant to write Xi. There is no F sub Xi. Yeah, right. Okay, so that's sort of almost a formal definition. Now, let me just now make a few formal, just slightly more formal and literally true statements in the form of a few definitions. So a chart, so this is just formalizing what we just said. A chart for a set M, which will be our manifold, of course, is a collection. What? Is it? I ran together, so it doesn't make sense. Is a bijection. In other words, it's a one-to-one mapping between the points of some subset of M onto, and here's where this word open actually gets used, onto an open subset of an open subset, which I'll call U tilde sub C. I should call this a chart C for a set M, is a bijection of some subset of M onto an open set sub. I should have given this name, some subset, not reading my own handwriting very well here, some subset which I've called U sub C of M onto an open subset U tilde sub C of an n-dimensional vector space, which I've called V sub C. Okay, that's the first definition. Second definition now, which I started to run together with the first definition, is that just that an atlas is a collection of charts. An atlas for M is a collection, which how do I write? Right in this sort of curly A collection for atlas, a collection of charts which cover M. In other words, I'll say in a second. Oh, I can't move this board. Yeah.
The definition of a chart, doesn't the bijection have to be continuous with continuous inverse?
Well, it would be, yeah. So I alluded to that before. It would be if we had started with a topological space M, but I haven't yet given M a topology. So we're going. This will be any set, but of course I'm going to make it into a topological space using the chart. So there will be a condition. The condition will not be on the maps between the manifold and the vector space, because it wouldn't have a meaning yet. But the consistency condition, which I probably should have said, but I will say in a second, is that this gluing map has to be continuous. So all the gluing maps must be continuous.
Okay, so you're going to be defining a topology based on the charts being your continuous functions and these sets being your new open sets.
On the gluing map, it's going to be based on the gluing maps being continuous maps. And then the open sets can be pulled back from the vector space to the manifold. And then it will be the case, as you said, that these bijections will then be homeomorphisms or local. They will be both continuous and their inverse will be continuous. So when I say that they cover the M, what I mean is that these domains of the charts, these U sub C's, cover the M. So I think pictorially it's obvious. The way to say that in a fancy mathematical language is that the union of the set of all the domains, so first I write union, and then I'll write the set of all the domains, C, or C in the atlas. So that means the union of all of those, that union equals M itself. Anyway, I think the meaning is clear. So the charts cover M, and now I've run out of space. such that here's the thing that responds to your remark, such that the transition maps are all continuous. So all continuous means, in particular, that both F C eta and its inverse, which is F eta C, is continuous. I won't actually define continuous because I think these are just vector spaces and everyone knows the definition of continuous in the case of vector space. If you like, you can always think of these as R4 and then just use the standard definition, epsilon delta definition of continuous. Okay, so this FC eta is called these patching, these FC etas have different names. FC eta are called gluing maps or patching, gluing map or patching. Very obvious. It's through those maps that we paste together the different portions of the vector space out of which we were building the manifold. We only need one more definition, which maybe I let this go. That we don't want, it's true that we built the manifold out of these neighborhoods, but we don't really want to regard the manifold, and we don't want to give any special significance to the particular choice of neighborhoods we made. If we glue it out of different regions, we still want to have the same manifold. So we need a notion of equivalence we need a notion of equivalence that will allow us to do that. And strictly that becomes a notion of equivalent atlases. The two different atlases for the same, let me give them a name. So two different atlases for the same point set M, the same set of points M. I'll call them A and A prime. Equivalent. This is a tricky thing. So what you really want, the intuitive idea is where they overlap, everything is continuous. But there's a quick way and tricky way of saying it, which is just that they're equivalent, if and only that their union is also an atlas. So in other words, if I take all the charts and lump them all together, I still have an atlas, and basically that's just asking that all the overlap maps that come in between the old and new charts also should be continuous. Then in that case we say A and A prime define the same manifold. And so that leads to the last definition, which is that a manifold, this is the fancy way of saying that, a manifold is point set M divided with an atlas modulo this notion of equivalence that I just said. So equivalent atlases, I'm just repeating this again, what I just said, define just the same manifold.
Another question.
Yes.
for your atlas, do all the charts have to go to the same dimensional vector space?
Well, actually, the way if you want to be really careful, then the way I've defined it, I haven't demanded that they all have the same dimension. But you can see that if this, so I could take two manifolds, say take a 2-sphere and a 3-sphere, and I could take the union of them, the disjoint union. I could just say that my space consists of them together, and then it would be, according to the definition of that I've just given, that would still be a manifold, but it's not the case that we actually intend. What you can see is that if what's happened there is that my manifold is disconnected, and I'll be actually implicitly assuming always that the manifold is connected. If the manifold is connected, in other words, well, I won't try and give the topological definition for that connected, but it basically means you can go continuously from any point in the manifold to any other point in the manifold by some appropriate path. If the manifold is connected, then it will follow from this. I mean, it'll follow from this condition that the dimensions of all the V's are the same. See, because any two V, you'll have a sequence of patches, and between any two overlapping patches, this has to be a homeomorphism, that is, its inverse and its both it and its inverse have to be continuous. And that can only happen if the two dimensions are equal.
Topologically?
Yes, sure. So there's no way I could take a one-dimensional manifold, let's say take a real line, a one-dimensional vector space, and a plane, and find the neighborhood in the line and the neighborhood in the plane with a one-to-one continuous both way continuous mapping between this and this. The defense way of saying that is dimension is a topological invariant. Of course, that's if you really have to prove that, it's a fairly, it's not at all a trivial theorem in some sense, but that's, I think it's intuitively evident. You can't patch together. Or another way of saying it, another way of thinking about it is, suppose I tried to make a manifold that was, I don't know how I'll draw it. So it's the union of a disk and a line, let's say. So I stuck the line to the disk and I joined them at one point. Then you'll note, if you try and convince yourself that you will not be able to find a chart for some neighborhood of that point where they meet. So, see, because the neighborhood of this is something weird. It's a disk together with a line. And there's no way that that disk together with the line can be realized as a subset, as an open subset of, in this case, it obviously would have to be a two-dimensional vector space. So you can't find a subset of the plane, an open subset of the plane that looks like an open disk together with a line sticking to it, an open line segment. So speaking of dimension, I should say that if the dimension of these charts, of these fields, as I thought, is n, then m will be what's called an n-dimensional, an n-manifold, or an n-fold, or an n-dimensional manifold. And we'll, in this course, essentially always we'll be taking a course that n equals 4. And I'll also, just since it came up, I'll mention it. I wasn't planning to mention it, but we'll assume that m is connected. That is, the manifold, once it has its chart, is connected. It doesn't consist of two disjoint pieces. So there's some other ways. Okay, so I guess that's the formal definition. So I should stop. Are there any more questions on the formal definition?
Are you saying all the charts are the same dimension?
Yes.
So if you have a sphere, this is a stereographic projection, right? And you have one thing that projects on the plane, right? You have the two-dimensional, and you have a point, which is one-dimensional.
Well, the point, if you do stereographic dimensions, so that's pointing out an important fact. The stereographic projection is not a chart, okay, because that's not a, in fact, that point, that North Pole goes to infinity, which is not a point of the plane.
It's a chart from the circle missing a point, and then you need a second chart to make the average.
Yes, it is a chart. If we leave out the North Pole, then
Right, that's what I mean.
Well, that's what you meant.
So like you would have a union of the two charts, one being like the point and then one being realigning is versus.
Not the point.
The point isn't in open format. It's not the open set we want.
In any case, even if you extend the chart, the circle is still fundamentally a one-dimensional object, not a two-dimensional object, because we can parameterize it by one coordinate only.
Yes. So what do you want to do this in one dimension or two dimensions?
Just one.
Just the one. So we have a circle here, and then we have this line, and now we're doing some sort of stereographic projection from the North Pole. So you're taking this point and mapping it to this point, and so on. The point maps to itself.
Right.
Is that what you're talking about?
Yeah, and so like the
So
two,
this-
sorry,
No, this is a perfectly fine chart. If we take U, so let's call this NP. So we take the domain U sub C to be the whole circle S1 minus the North Pole.
yeah,
So we have to leave that out.
I agree. And now our two charts are just the one point and
No. So that was not a good chart because that's not a dimensional. That's not an open set. So what you have to take. So if you want a second chart, so we haven't quite covered the whole thing. So if we want a second chart, the simplest way is to just leave some other point out. So we could do stereographic projections from the South Pole, for example, and that would give us a second chart. And then what it amounts to is we're building the sphere, the circle in this case, by gluing together two open sets that basically look like this. So you could leave out just that point, or you could leave out a whole segment and so on. But as long as you cover the whole circle. Any other questions? So now, so you might, if you think about what we've just done, you might feel, oh, that's strange. He didn't mention coordinate systems. How come? Where do coordinate systems come in? And they come in just as a special case of a chart. So suppose B sub C, now the vector space. I was careful. You might wonder why I kept calling it a vector space, why I didn't just say R sub 4 all along. I did that because it's in the spirit of the equivalence principle. The equivalence principle is telling you that space-time is locally like Minkowski space. Minkowski space is not R4, because R4 comes with distinguished coordinates. I mean, R4 is defined as the set of quadruples, x0, x1, x2, and x3. So it's born with Cartesian coordinates. But Minkowski space, and it has an origin, for example, where they're all 0. But as we know, in special relativity, Minkowski space doesn't come with a distinguished origin. There's no magic point in space-time, flat space-time. It's the origin, different from any other. Nor is there a magic set of coordinates. There's no distinguished time-like direction. That's the principle of relativity. That the structure which it is has the full Poincare group as a symmetry. So that was the motivation for doing that. But now in practice, a lot of times you will be dealing with coordinate systems. So how do we relate coordinate systems to chart? Well, in this case, let P be a point of our manifold. Then C be a chart, and C of P will now be, if we choose, if the vector space associating with 2, it is R4, it'll be an element of R4. In other words, C of P, what is an element of R4? It's just a set of 4 numbers. It'll be a set of 4 numbers, x0 of P, x1 of P, and so on. And these 4 numbers are called coordinates, of course. And so each one of them, taken by itself, now maps. So here's my manifold M. I had mapped it into R4 by this some subset of it by this chart map C. But then R4, from R4 I can just get, like if I just focus on x0, let's say the time coordinate, then I can, let's call it the time coordinate. It's just some number, some one of the 4 coordinates. It just maps to R, a single R. So the net effect is that I have just a scalar function on the manifold M to R, and that's what we call a coordinate function. So a chart on R4, a chart such that B sub C equals R4 is equivalent to 4 coordinate functions, x0 to x3, all of which map M on M. In other words, if the function x mu maps the manifold M to the real line R, it gives you a number for every point. So a chart in this sense is what's called a local coordinate system. It's local because it doesn't cover, like we saw in the circle case, it doesn't cover the whole manifold. So another way of saying this is that Rn in this case, it comes with coordinates, and we just use the chart to pull those coordinates back onto a portion of the manifold. So we can okay. So I don't think any more needs to be said about that. So if you were to draw a picture of what the coordinate system looks like, here's our manifold M again. I don't know if everyone's then, and here's this region within it, which is the domain of the chart. And then if this was a coordinate chart, in other words, a map to Rn, then we would get a local coordinate system with some curvy thing like this, covering that region. These are the coordinate grid, where these are the lines of constant coordinate. You know what I mean? So I think that's the only thing. I just want to add a couple of technical conditions, and then we'll finish. So these are even more somehow special. I mean, more obscure, but just than the question that came out about the dimension being the same. But just to be correct, I want to say. So I said that I wanted to say that the manifold should not be disconnected. But if I don't say that, there are pathological things that satisfy these definitions that are not what's called paracompact. So the way, I'm not going to define that, but if you ever look in a more mathematically oriented book on relativity, you might see that space-time is defined as a paracompact Hausdorff manifold or something like that. And for us, all it means is this. Which no one would ever, you'd never, unless you tried very hard, think of a counterexample to this. But there exists a countable, I'll assume that there exists a countable address for M. In other words, I don't need more charts than I can label by the integer. That's related, or assuming connectedness is equivalent to what's called and M should be paracompact. And the second thing is what's called Hausdorff, and this, so that's the first extra condition. And the second extra technical condition is for all pairs of points in the manifold, which are distinct points, I can find two charts. I can find an atlas, so there exists an atlas, and within that atlas, two charts which are disjoint and contain P and Q. So that P and Q are in disjoint charts. So what does that mean? So here's the manifold. Here's P is Q, it means I can find some atlas in which there's two different charts. C and eta, let's say, such that this is U C, this is U eta, such that there's no overlap between U C and U. That rules out certain kind of topological examples that you wouldn't want to call a manifold. Like you take the real line and you take the origin twice. So anyway, we could discuss if you're interested in these kind of counterexamples. I can discuss later. Was there a question?
Yeah. So in the beginning, you said you talked about mappings to vector spaces and not R4.
Right.
But then you also talked about open sets in these vector spaces. So it means you must have some notion of distance.
Ah, yes. Well, not distance. So that's the subtlety of a topological space. So the vector space has a topology. It comes with a topology, but not with the notion of distance.
Any vector space comes with it.
Any, let's say, any finite dimensional vector space, which is what we always have here, comes automatically with the notion. So that's a good question. So I was presuming that, which maybe was not really fair, but I'm pretending that it's fair anyway. So any finite dimensional vector space does come with a topology. And the reason is basically you could put any metric on it, any positive definite metric on it you like, and take the open balls of that, and you would find, or take the notion of convergence associated with that distance, you would find that a sequence converges in one choice of topology if and only if it converges in all the other ones, as long as you're in finite dimensions. And the intuitive reason is that what do different metrics mean on the same manifold? They mean, I'm running out of space. So a metric is basically, if we think of a vector space, it's basically just telling you what the unit ball is. Once I tell you what the unit ball is, I know what the metric is. A different metric, because of the linear nature of the vector space, it doesn't look like, with respect to the first one, it doesn't look round anymore, but it's still an ellipsoid, and it's still some finite size. So given any one of these round neighborhoods, let's start from a bigger picture, given any one of these round neighborhoods, I can find within it, I mean the ellipsoidal neighborhood might be stretched, but I can take it arbitrarily small. So I can find within it some ellipsoidal neighborhood of the origin, let's say. And within that, though, I can find an even smaller round neighborhood. So the neighborhoods are, whatever the right word is, they're nested in such a way that each one of the one contains an infinite numbers of its own sort and all the other sort. So then if you think what that means, it means that the sequence converges to the origin with respect to the one metric, the one set of neighborhoods, if and only if it converges with respect to the other set. That's a pictorial way, but you can...
You're assuming that these vector spaces are real or complex vector spaces.
Real, I should have said. They're all real vectors. So this is a four-dimensional real vector. But real vector. Okay, so let me just write out the definition, the summary, and that quit. So the summary is now that we have a fancy language, M is a paracompact allotrope C0 and most of this course, and I didn't try and define what's called a manifold with boundary, which is important in some cases, but so what I really defined is a manifold without boundary. And the dimension is dimension 4 usually. If we talk, for example, about fluid Klein theories, then we'll take a different dimension. But in general, we'll be thinking of dimension 4. So that's just the formal summary, but the important thing is to understand what it means. It really means that it can be built by patching together these neighborhoods taken from a four-dimensional vector space. And then we'll use exactly this. It'll now be a very short step just to define what is a differentiable manifold. Then we'll have the notion of tangent vectors, tangent spaces and vectors. And from vectors we'll have tensors and so on.